to say, okay, so here is the solution, since apologies for the people in person to repeat a little bit, but so we want to find the image of this vector, but H takes us from vectors in the standard basis to the standard basis. So I just do matrix multiplication and find that this matrix times 2, 3, do the arithmetic, gives me 11, 16. Because this is standard basis, the result is in the standard basis, which is what I want. And so this is the answer. This vector here, this is the image. And to sort of see how that works in detail, we can ask, what is the formula for the map? Well, we can do that by saying, well, we know that this is constructed, right? The matrix H, 1, 3, 2, 4, maps any vector to its image, right? So what is this image? So to solve the problem, what is the formula? You just, instead of doing a particular one, 2, 3 here, you do the general X and Y, and then you get X plus 3Y up top, and in the second component, 2X plus 4Y, so that H sends XY to X plus 3Y to X plus 4Y. And implicitly in this definition, this is in the standard, I've only got a vector here I have to specify in some basis. And so when I give a formula like this, unless I give subscripts here to indicate what the basis is, you just assume that they're standard basis elements, okay? And then if I go and apply this directly to the vector up here, 2, 3, right? Well, that's going to be sent to, so its image is 2 plus 3 plus 3. And the bottom one is 2 times 3 plus 4 times 3, which should equal 9 plus 2 is 11, and 3/4 is 12. Oh, wait a minute. This is 2 here. I just misapplied this. The X is 2, and so I'm putting in 2 times 2 plus 4 times 3, so 3/4 is 12. 2 times 2 is 4, so I get 16. So you can see I get the same thing as up here. So, and this has just been a range. I mean, in some sense, you've defined matrix multiplication to be congruent with this kind of map action. Okay, so that the way matrix multiplication has been defined, it obeys linearity. So the matrix multiplication was defined so it respects linear combinations because it produces linear maps, which isn't obviously apparent from just the definition, but you can sort of see that what it does is it's going to take an X component and a Y component and give you a linear combination of those. So matrix multiplication just gives you a linear combination over here in each component. That's why that turns out to be why it's linear. Okay, so there is sort of a review question. Are you guys okay with this? Any questions or you're okay? So here's maybe a little bit, let's go to 24 and try 24. This one is a little, one of these ones that you sort of like strikes fear in your hearts because it involves polynomials. Right, so this is, let me write the problem down here. This is on page 386, and we're going down to problem 24 here. And it says we're given a vector v as 1 plus 2x, okay, and with the let's call this w, and we have a map. Let's see, let's give the map a name. Let's call it J, which is a map from R3C to P2. I never can tell whether for the polynomial, should the 2 be down here? I'm going to put it up top. I'll have to go through and correct the text, so it's always at the top. Because they're polynomial exponents, so it makes sense to put it up top, and then it'll be parallel to the 3 up here. Okay. So the question is, this is a member, we're thinking of this as a member of P2, the quadratic polynomials, okay? This is the space of quadratic polynomials. And decide whether this vector is in the range of the map from R3 to P2, which is represented with respect to, so we're using for the domain, we're using E3. That's the standard basis, but for the codomain, we're using 1 plus x squared and x, which is not the standard basis for this one. So E3 again is going to equal 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay? So we have, and the map is given, we have capital J equals 1, 3, 0, 0, 1, 0, and 1, 0, 1. So the question is this vector 1 plus 2x in the domain, in the codomain, is it an image of some vector? Is it in the range of the map defined in this way? Where this J here, let me put the subscripts on, J takes vectors in the standard basis to representations of vectors in P2 in this basis D here. Okay? So, how are you going to decide that? The first problem is to sort of think, now let's see. Oh, good, I am recording. Okay. The first thing is to sort of think, how could I decide this? Well, it's sort of the problem is, it's sort of the opposite of the problem of finding what the image is. We could put in, a domain vector, like a 3-component vector in R3C, an arbitrary one, and then find what the image is, right? And then this question is whether this vector is going to be in that image. Now, the problem is, one thing we can do right away is say, well, we have this image in P2, but we can also find what its representation is in this representation here, because then we'll have its representation as a 3 vector. And so to solve the problem, we won't have to think, maybe except at the end, about the polynomial aspect. So that sort of translates the problem uniformly into 3 vectors rather than with the polynomials. So task A here might be, what is W sub D? What is this vector here? In this basis, what's the representation of the vector D in this basis? So why don't you just try to solve that problem first? Part A, which is let's represent W in terms of this vector here. And then when you can either raise your hand when you've solved the problem or when you give up. So that means everyone can raise their hand, right? Because you're either going to give up or solve the problem. Let me